This is the lecture on convergence for Friday, September 9th. So this is convergence part 1 on the Notes on Fourier Series, chapter 5 by Harvey Seeger. So this is slide L04. So we want to talk about piecewise smooth functions today. For a Fourier series that's generated from a function, for it to converge and for it to converge to the function, we need certain properties. Continuity is not enough. And so just as a reminder, we say a function is continuous at some point x equal to a if this limit, the limit of f of x as x approaches a, is a true statement, equals f of a is a true statement. Now here, remember, we're saying three things. The first thing we're saying is that the right-hand side is defined, that is, f is defined at the point A. So f of a is a finite number. We're saying the left-hand side, which is a two-sided limit, that exists. So the limit from the left equals the limit from the right, and they're both equal to a finite number, the same finite number. And finally, we're saying the limit that you see on the left side, which is some finite number, and the function on the right side at a, which is some finite number, they're equal. They're the same finite number. So that's our definition of continuity. And so now we define what it means for a function to be piecewise continuous. So a function is said to be piecewise continuous if the function is defined and continuous at all but finitely many points. So there may be, in this case, I just said capital N points x sub I in the interval where the function is not continuous there. And so at those points, we allow only either a jump discontinuity or a removable discontinuity. What we do not allow are infinite discontinuities. So no infinite discontinuities. We also require that the function is what we call right continuous at the left endpoint and left continuous at the right endpoint, just that the limit as you approach the endpoints are equal to the function value at the endpoint. So, for example, we could have, a function like this. So that's A, B. So if we have a function so for piecewise smooth, I'm going to have to color these endpoints in. So that's what that limit means here. And here for piecewise smooth, I need this endpoint colored in. That's what this other limit's saying. And so here, this would be piecewise continuous function because where it does have a discontinuity, that's just a jump discontinuity. What we don't have is like a vertical asymptote. So a function like this, so there's A, there's B, we have a function like this. It just goes up forever, and there's an asymptote here. So then that's going to be an issue. That's not going to work out. So here, assume there's a vertical asymptote. So here, the presence of the infinite discontinuity, is outside of what we allow for the definition of being piecewise continuous. So now, what we're really interested in is this notion of being piecewise smooth. So a function f of x is said to be piecewise smooth, or perhaps more technically correct is to say piecewise C1. but we'll just say piecewise smooth. So a function is said to be piecewise smooth if and only if both f of x and f prime of x are piecewise continuous. So f of x is piecewise smooth on this interval a to b, on this closed interval a to b, if and only if f of x is piecewise continuous on the closed interval a to b, and f prime of x is piecewise continuous. So here, when we say piecewise continuous, we're talking about a function that is defined and continuous at all but a finite number of points, where we only allow a jump discontinuity or a removable discontinuity. So the main thing is we're simply not even allowing functions that have infinite discontinuities. So if a function is piecewise continuous and its derivative is piecewise continuous, then that function is said to be piecewise smooth. So at the end of the day, this is the big definition that we want, because the definition for piecewise smooth, because these are the types of functions that we will be applying Fourier series to. So we're basically just not allowing infinite discontinuities. And just an FYI, we say a function is continuous piecewise smooth. So here I've added this extra term, continuous piecewise smooth, if number one, the function is piecewise smooth. So the function's piecewise continuous and its derivative is piecewise continuous, and the function has no discontinuities. So here the function we said is required to be piecewise continuous. Here it's a little bit stronger. Here the function is actually just straight up continuous. So continuous piecewise smooth is if the function is continuous and the derivative is piecewise continuous. Now, maybe I should draw a picture here real quick. So make some room. So here, like here's the axis here. So a function of this form, for example, so I'm just kind of making this up. I'm going to color in this end because I want it to be piecewise continuous. So something like this. So there's a jump here. And there's a removable discontinuity. So I've just kind of made this up. So here's B, here's A. So we ask, oh, is a function like this, is this function piecewise smooth? That's the question. So for it to be piecewise smooth, we need to check if the function is piecewise continuous and if its derivative is also piecewise continuous. Okay, so here the function is continuous and defined, and at the endpoints it's continuous. So that's part of the definition here at the endpoints. And where it's not continuous, so for example, right here and right here, we have a jump discontinuity and the other one's a removable discontinuity. What we do not have is an infinite discontinuity. There's no vertical asymptotes or limits that go up forever. So the function is piecewise continuous. So what about the derivative? So here we can think about the shapes here. So I'm going to draw the derivative in blue. So here the function is increasing. So the derivative between these 2 points, between A, and I guess I'll call this C. I'll call this D, I guess. So between A and C, the slope's always positive. It's some positive number. I don't know what it is. I'm just going to graph it as being some positive number. Between C and D, it's still a positive number. Could be a different number. Could be the same number. I'll just make it a different number. Could be the same though. Here, even if this were colored in, so you can see, even if this was colored in right here, the derivative would have a jump. So here, the slope is now negative. So between B and D, the slope would be some negative. And so this blue curve, that's the graph of the derivative. The blue curve is F prime, and the red curve is F. Oops, not F prime. And so here you look at the blue curve, that's the derivative. That's continuous and defined. Where it's not continuous, we either have a jump discontinuity or removal. Here they're all jump discontinuities. And there's no issues at the endpoints. So yeah, in this case, this red curve that I drew would be piecewise smooth. So perhaps that's an example to rewind and watch again. So clearly note that f prime will not be continuous wherever f of x is not continuous, because to be differentiable, if it's not continuous, then you're not going to be differentiable at that point. So here, that's certainly true, but f prime may have some other points where it's not continuous. Just as we saw in the previous example, at any corner of f of x, the derivative is not going to be continuous there. There you have the derivative from the left and the right won't be equal. If you think about the absolute value function, that would be an example of a function that's continuous piecewise smooth, the absolute value function. If you think about the graph, it's just that V shape for the absolute value. So the actual function, yes, I know that's a terrible graph. The actual function it's continuous. It's more than piecewise continuous. It's just flat out continuous. But the derivative has a discontinuity, right? The derivative here, the slope is negative, so it'll be some negative number, and here the slope's positive. So you see the derivative has this point of discontinuity at 0, but the original function is continuous at 0. So the derivative may have its additional own, discontinuities depending on the shape of f of x. And just a comment here that if the derivative is piecewise continuous, then f of x is also piecewise continuous. And I say why here. The main justification is to remember from Calc 1 that differentiability implies continuity. So here, if we say f prime is piecewise continuous, among other things, we're saying the derivative exists. If the derivative exists, f of x is going to be continuous. So certainly wherever f prime of x is continuous, the function will be continuous, and f prime of x won't have any infinite discontinuities. Therefore, f of x won't exhibit any vertical asymptote behavior or anything like that, because we're just not allowing those types of features. So think about what happens if the derivative is infinite or negative infinite. So the main takeaway is the definition of piecewise smooth, which I'm going to highlight again. So f of x is said to be piecewise smooth if both f of x and f prime of x are piecewise continuous. And this is on a closed interval a, b. And piecewise continuous just means the function's continuous, except at possibly finitely many points. And where it's not continuous, it either has a jump discontinuity or a removable discontinuity. But what we do not allow are infinite discontinuities, no infinite discontinuities. Okay, so some quick examples of functions that are and are not piecewise smooth. So because of the boundedness restriction that we don't allow any infinite discontinuities, obviously it's easy to find examples. So for example, 1 over x in the interval -1 to 1, even if we remove 0, this cannot be piecewise continuous because the limits at 0 blow up. So as you remember the graph of 1 over x, so here I'm going to restrict the domain to -1 to 1. And the graph looks like this. And so this infinite discontinuity here is a problem. This whole section here, that's the issue, where it's blowing up on either side. So that, because of that, 1 over x is not a piecewise smooth function. So what if we look at sine of 1 over x? So here, there's no issue of the function blowing up. Sine is always bounded. But here, the actual limits don't exist. So this is a Calc 1, kind of, I guess, just to remind you that when we take the limit of 1 over x as x approaches 0, the two-sided limit does not exist. A mistake in Calc 1 is sometimes in haste, one might say the limit of 1 over x as x goes to 0 is infinity. That's just not true. What is true is that the limit of 1 over x as x approaches 0 from the right, that's a plus infinity. And here, the limit from the left would be negative infinity. So in this case, if we take the limit from the right, we're basically doing sine of plus infinity, and so sine just oscillates forever. And here, that's going to negative infinity. And so that oscillates forever. The two-sided limit of 1 over x just doesn't exist because the right and the left are doing two different things, not to mention they're blowing up to infinity. So here's so those are more kind of, analytic examples, just to sort of where the denominator blowing up is an issue. So here's kind of something that's a little more standard that, we might think, oh, this has a chance of being piecewise smooth. So this is the absolute value of x raised to the 1/4. So first thing I would recommend is, think about the definition of the absolute value, right? So absolute value of blah is going to be just copy down blah if the thing between the absolute value bars is greater than 0. And absolute value of x will be negative x if x is less than 0. So here we see the definition of absolute value of x to the 1/4 is x to the 1/4 if x is greater than 0, and its quantity negative x to 1/4 if x is less than 0. And remember, negative x is not a negative number because here x is less than 0. So negative x is actually positive. So now we take the derivative. What we're going to do is use a power rule and take the derivative of each piece. So here, bring the 1/4 down, times x to the 1/4 minus 1. 1/4 minus 1 is a negative 3/4. And for the derivative when x is less than 0, we need a chain rule here because the inside function is a minus x. So the derivative of the outside, as before, we bring the 1/4 down. 1/4 minus 1 is a negative 1/4. Now the derivative of the inside is a minus 1, and that's where this minus sign is coming from. The last part, when we do a derivative like this, is we have to be careful at where the function changes definition. So here, the function to the left of 0 has a different definition than to the right of 0. So I have to be careful. At 0, the derivative is only defined if the two-sided derivative is only defined if the derivative from the left and the right are equal. So here, at 0, there's a big problem because this x to the negative 3/4, that's in the denominator. So at 0, we have, a vertical asymptote of the derivative here. We have a place where the derivative is blowing up to infinity. And in the other case as well. So here, the original function is continuous. You can think about the graph. So what would the graph look like? So this is the original function. the fourth root of x, it's kind of like a square root. And then if x is less than 0, we're doing negative fourth root of x, and that negative x reflects it about the y-axis. So that's what the graph looks like. So the function f of x is piecewise continuous, but the problem is the derivative. The derivative has an infinite discontinuity, and it's because of this right here at the origin. You can see there's a vertical tangent. And so that means the derivative is blowing up to infinity. And so that's the problem with the derivative. The derivative is not piecewise continuous. Therefore, this function is not piecewise smooth. So here, we're halfway there. F of x is piecewise continuous, but f prime of x is not. And so the original function f of x is not piecewise smooth. Take a look at the absolute value function. This is an example of a function that is piecewise smooth. The original function clearly is piecewise continuous. In fact, in this case, it's stronger than that. Here, the original function is actually continuous. It's stronger than piecewise continuous. And the derivative, you can see, has a discontinuity, but has no infinite discontinuity. So the derivative is, again, itself piecewise continuous. So both f of x and f prime of x are piecewise continuous. So f of x equal to absolute value of x is piecewise smooth. In fact, it's continuous piecewise smooth because f of x is continuous. So let's see why we require more than just continuity. Let's see why we require piecewise smooth as we go through the proof here for showing, piecewise smooth functions is what's required. So, okay. So we want to start to talk about function adjustments that are required so that if we start with a function and make its Fourier series, we have a Fourier series that makes sense in terms of periodic extensions and everything like that. So before getting started, note that for our Fourier series, which is right here, we want all of the terms, the coefficients, to be finite. So a very first and basic requirement is that a sub 0 be finite. Now, remember, a sub 0 is an integral. A sub 0 is just the average value of the function. So a sub 0 is this integral, 1 over 2L integral minus L to L. And in here, I just have the function f of x. So right off the bat, we see why we would need f of x to be piecewise continuous. To be able to integrate f of x here, our Calc 1 theory says f of x has to at least be continuous or piecewise continuous. In Calc 1 is the weakest type of function that we can integrate. Anything less than that, we're not sure if we can integrate it. So this right off the bat is why we would need f of x to be piecewise continuous. So the second question is, well, why do we need f prime of x to be piecewise continuous? So keep that in mind, and we'll get to that in a second. So yeah, so we have some restrictions that we want to put on f of x. Okay, so this is for functions that we want to take Fourier series of. So here we're starting out with a function that really has no restriction. So we say, just suppose f of x is a real function. So here there's no restriction. We're not even saying continuous yet, not saying anything. That'd be a real function defined on this interval minus L to L. So now the restriction we have depends on the behavior of the function at the endpoints. So case 1 is if f of negative L equals f of L. You think about the absolute value function, it has that on a symmetric domain. Then here's the restriction. So now we're bringing in what we call a regularity restriction. So regularity refers to if a function is continuous or differentiable or whatever. So here we require the periodic extension of the function f of x to be piecewise smooth. So This is so that when we, you know, this is about the periodic extension making sense, and we'll show why just to be able to get a sub 0, we need f of x to be piecewise continuous. And I'll show why we need f prime of x to also be piecewise continuous in a second. So here, this is one of our restrictions, that this is the only kind of function we want to try and take a Fourier series of. And the other scenario is if the function is not equal at the endpoints, then we first want to what we call adjust the function. So we're just going to redefine it, or some books use the term adjust the function at the endpoints. This is so that, if you look at the periodic extension, if you look at the Fourier series, it does certain things naturally at the endpoints. And we talked about that last time in lecture 3. So we talked about how at the endpoints, because of periodicity, the Fourier series, its inclination is to average. And so here, if I want to make a sentence, if I want to say, oh, the Fourier series of this function converges to, then the correct sentence would be, I want to say it converges to the periodic extension. And so here we want a well-defined periodic extension of the function that we're starting out with. So here, if the endpoints are different, we're going to redefine the function, or sometimes it's known as we're going to adjust the function, redefine it at the endpoints, at the left and right endpoints. We redefine the function to be the average of the original left and right endpoints. So by way of an example here, let's look at the function just y equal to x. So here's y equal to x on, I'm going to draw an axis here. Here's the function y equal to x on just some interval minus L to L. As we saw last time, the periodic extension would not be well defined, because what we would have theoretically is, in the periodic extension, would be a function that has one output, that has two outputs for one input. So here, at these points where the domain is ending, so that's negative L, and this is L. At these points here, there's an issue with the periodic extension. More than that, it violates the vertical line test, is just that a Fourier series would not give you two outputs for one input. It just violates the way a Fourier series would behave, because a Fourier series is a function. So a Fourier series will never converge to a function that looks like this. It would converge to a function that looks like this, though. So here now, if I average these endpoints, darker blue here, if I average these endpoints and use that as our function, where it's f of x equal to x inside the interval, and it's 0 at negative L and L, then that's the type of function that a Fourier series could converge to. And we talked about this example last time in lecture 3. You can take a look at those lecture 3 slides for the Fourier series of y of f of x equal to x, and in particular, look at the behavior at the endpoints and see what the Fourier series does. So actually, restriction 1 to me is just kind of a special case of restriction 2, because here, think about what happens if f of x, f of negative L is equal to f of L, and we still use this correction. So here, if f old will just be f of negative L, and f old of L will just be f of L, it'll just, when we add the two, since they're equal, you'll get 2 times f of L, divide by 2, you'll just get f of L. So we can use this averaging definition whether the endpoints are equal or not. It'll work in both cases. When the endpoints are equal, it'll just spit out the original endpoints. When the endpoints aren't equal, it'll average it. And that's what we want, because that's the kind of function the Fourier series would converge to, because of its, tendency to average and smooth things. So here at the endpoints, because of the periodicity, it has this tendency to average. So as I said, some books refer to this function now as the adjusted function, and you could introduce new notation, f bar. And now we would look at the periodic extension of f bar. And so the periodic extension of the adjusted function, now, we would indicate as f tilde of f bar of x. So you start with f. If the endpoints are different, you adjust it. So then you get f bar. So now the endpoints are the average values of the original endpoints. And then you periodically extend it. And so just so that we don't have too much cumbersome notation, we're going to not write the bar anymore. So we'll just write f tilde of x. And this will represent not just the periodic extension, but the periodic extension of the adjusted function, where we're averaging the function at its endpoints, whether they're equal or not, it's the same outcome. So now we claim, with this restriction in place, plus requiring the functions to be piecewise smooth. So here, once we've adjusted the function, we then require the periodic extension of the adjusted function to be piecewise smooth. So here, there's basically two conditions that at the endpoints, we have the averaged value. And the second condition is that we have piecewise smooth functions. So here we require the periodic extension when you just look at it between minus L to L to be piecewise smooth. Because it's periodic, that piecewise smooth behavior will then just repeat itself to, from negative infinity to infinity because of the periodicity. The behavior on minus L to L is kind of a microcosm that's just then repeated to the left and right. So these are restrictions, the piecewise smooth and the averaged endpoints. And so we claim this will be enough to guarantee, we need at least this to be true, that the absolute value of a sub 0 is finite. And we need that the sequence terms go to 0 as n to go to infinity for convergence to even be possible. Now be careful. The sequence terms going to 0 is not enough for convergence, but it's necessary. So here in this lecture for convergence part one is just proving that convergence is even possible. So we need to show the sequence that the coefficient terms go to 0 and that a sub, that all the terms are finite, not just a sub 0, but all the terms have to be finite. So let us now start to establish those facts. The first claim is that any function defined on minus L to L that satisfies restriction 1 and or restriction 2 form a vector space. So just remind you, basically the restriction is the periodic extension needs to be piecewise smooth. That's true in both cases. And at the endpoints, we want to use the averaged value. And so whether it's equal or not, we want to make sure we've redefined it or adjusted it so that at the endpoints, we're using the averaged value. So those are the restrictions. So yeah, we claim that the set of functions that satisfy restriction 1 or restriction 2 form a vector space. So what does that mean? Anytime someone makes a claim that something's a vector space, you want to identify a set, because we're talking about a collection of objects. Here it's functions. Here we're specifically talking about functions defined on minus L to L that satisfy restriction 1 and restriction 2. So now the vector space part is you can take two functions of this kind and add them, and you should get back a function of the same kind. That is, if I take two functions that satisfy restriction 1 or 2, add them together, that sum should again satisfy restriction 1 or restriction 2. And if I take a function that satisfies restriction 1 or restriction 2 and multiply by a constant, then again, that new function will satisfy restriction 1 or restriction 2. So here, mathematically, I can say the vector space argument is that if f of x and g of x satisfy either one of the restrictions, then we claim that any linear combination will also, any function formed that's a linear combination of these functions will also satisfy restriction 1 and restriction 2. So I'm going to let you think about it, because this is more a vector space theory, linear algebra thing. So I'll let you think about the proof of that. It's for claim 1. So now here's claim 2. If f of x satisfies restriction 1 or restriction 2, then there exists a finite positive number capital M such that the absolute value of the periodic extension is less than M. So here we're saying that for the periodic extension, so if I have some periodic extension, I'm just going to make up something here. If I have some periodic extension, it's saying there exists a number capital M such that f of x will be between m and negative m. So here we have sort of this upper bound and lower bound, which is capital M and negative M. Capital M, negative M, and here's the function f of x in between. So this is really not that surprising, because if you satisfy restriction 1 or restriction 2, then you're dealing with a function that's piecewise smooth. So here, we don't even need to worry about f prime. This is just a result about f. So here, we know f is piecewise continuous. So what does that mean? It doesn't have any infinite discontinuities. We're basically saying it doesn't blow up anywhere. We're not allowing it to, because any function that has infinite discontinuities is not piecewise smooth, wouldn't satisfy restriction 1 or restriction 2. It wouldn't be something we would be talking about here. So we've specifically taken out these functions that cause trouble. Now, from a technical point of view, in general, if you have a continuous function or piecewise continuous function that's defined on a closed interval, then what we're saying is, when you say defined, you're saying f is defined for all of those values. F is defined at A, f is defined at B, f is defined at every point in between. And the word defined means it's equal to a finite number. From an analysis point of view, in analysis, this closed interval is what's known as a compact interval. And we can show for compact intervals, continuous functions are bounded on compact intervals. And if you're not taking analysis and don't know what compact is, it doesn't really matter. It's the main idea is the continuity here forces the function to be defined at every point in the interval. The problem with the 1 over x example is it's defined on an open interval. So if you look at this function 1 over x, I can't define it on any interval that contains 0. If I want to define it, at best I can define it, I'd have to use an open interval here on 0. I could close this end, but I can never have a closed interval where we're including 0 as part of the domain. It's just not possible. So, because f of x, the 1 over x is not defined at 0. So by definition, you say a function is defined at a point, you're forcing it to be finite. So here, we can extend it, if I know that, if you now look at the periodic extension or the adjusted version of the periodic extension, so this is if it's restriction 2, and if you look at just minus L to L, again, the behavior of the periodic extension in minus L to L is mirrored in, because of the periodicity throughout the entire real line. So here, the periodic extension was required to be piecewise continuous. So again, the continuity on a closed interval, again, implies that the function's defined at every point. It's not blowing up to infinity. We don't have one of these cases where it's going to plus infinity like 1 over x. That class of function is just not allowed. And that's not good or bad. That's just the way a Fourier series. We're kind of learning the behaviors of a Fourier series, what are its limitations and what are its advantages. And so, it's not good or bad, it's just what it is. So a function like 1 over x, we want to be careful if you take the Fourier series of that. You want to be careful what domain you're looking at. You want to, think about all these issues. It may not be ideal. So yeah, so if a function satisfies restriction 1 or restriction 2, then we claim that the absolute value of the periodic function is bounded. That is, this is a function that's not going to blow up to infinity anywhere. So this will be important. We'll use this in the next two parts here. Okay, so now the third claim. So if f satisfies restriction 1 or restriction 2, then, so if f of x satisfies restriction 1 or restriction 2, then we know there's going to be a positive finite number, capital M, such that the absolute value of the periodic extension, or the periodic extension of the adjusted version of f of x, is going to be less than M. Then we claim that the coefficients are also going to be less than M, or 2M. So a sub 0 we claim will be less than M. Absolute value of a sub n will be less than 2M, and the coefficients of the sine Fourier basis, of mode n will also be bounded by 2M. Remember, what we want to show is that these coefficients go to 0. If any one of these coefficients does not go to 0, then convergence is not even possible. So this doesn't show that they go to 0, but this shows that they're bounded. And so this is a good first step. And so, so there's 4 claims here that I want to prove. The fourth claim will finally prove that a sub n, b sub n, they go to 0 as n goes to infinity. Again, that doesn't prove convergence, but that proves convergence is possible. So first we show that the coefficients are bounded. It's really important that none of these coefficients is equal to infinity or something like that. Then the Fourier series is totally meaningless. So here we first show that they're bounded. And here there's a very, 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 very important inequality that I want to show you. And this is extremely important. So as you know, we can always write that a number is greater than the negative of its own absolute value and less than or equal to its own absolute value. And I'll let you think about that. If a is positive, then obviously it's greater than the negative of its own absolute value, and it'll be equal to its absolute value. If a is negative, then clearly it'll be less than its own absolute value, and it'll be equal to the negative of its absolute value. That's all just by definition. So now let's replace the a with some real valued function f of x. So here I've just replaced a with f of x. Now we're going to integrate. So integrate all sides of the inequality from minus L to L. So now I integrate. Okay, so now let's look at what we have. We have this equation. And so I want you to remember when we studied the absolute value, like back in a pre-calculus class, you remember we said, so let me make some room here. We said that if we write this, if I write, I'm going to say capital A less than or equal to capital B, and here greater than or equal to negative B, well, then that's the same as just saying absolute value of capital A is less than or equal to B. And so now I want you to look at this equation we have written below. The A is this integral right here. Here's B, and here's negative B. So what I can conclude that the absolute value of A, the absolute value of this thing is less than or equal to B. And so that's what I have in this next equation here. Here's the absolute value. So this term, the absolute value of this term is less than or equal to this term. That's just the definition of the absolute value that, using properties. So this inequality is super important. It's super important in this class. It's super important in an analysis class. And what you should see basically is that we're quote unquote bringing the absolute value inside. And so the integral of the absolute value is less than or equal to, the absolute value of the integral is less than or equal to the integral of the absolute value. That's what the inequality is saying. So I'm going to ask you to remember this because we're going to use this over and over and over and over and over again. And so take a look at these steps here. It's just, a lot of pre-calculus, but it gives us a very powerful. So you start from there, then you replace A with f of x, then we integrate, and then we say, oh, well, this is just the definition of, the absolute value of something being less than a number. And so now let me use this property. Let me start with a sub n. As you remember, we have the projection formula here. F being projected against the basis element and then being normalized. So now I'm going to use this property. So now I'm going to bring the absolute value inside. You can pull out the 1 over L, it's positive. And when I bring it inside, the original is going to be less than that thing. So here's less than, and look at where the absolute values are now. Pay attention to the location now of the absolute value before, and here I broke up the product. So we know that the absolute value of A times B equals the absolute value of A times the absolute value of B. So here I kind of did I did two steps in one, so watch out for that. And so what are the two steps? So the first step is I brought the absolute value inside. So we had absolute value here and an absolute value here. And then I broke up that term into the product of two absolute values. And so I'm able to bring the absolute value inside and say less than or equal to using this identity, which we proved here up here. Now I'm going to further bound the function. So absolute value of cosine here is going to be less than or equal to 1. Less than or equal to 1. So I'm going to bound the function. It looks like I made it disappear, but really there's a 1 written right here. And I'm saying absolute value of f times the absolute value of cosine is less than the absolute value of f times 1, and then you can integrate both sides and the inequality is still true. Finally, we use the fact that the absolute value of f here, that this is a bounded function. Because this is piecewise continuous, we know f of x has no infinite discontinuities, and that it's defined at every point where it's not defined. It either has a jump discontinuity or removable discontinuity. There's no infinite discontinuities. We know there's a number m such that absolute value of f is less than m. And so here I've bounded the absolute value of f with its upper bound m. This is a constant. M is a constant. So I can pull m out. You get m over L, and then we're just integrating 1 dx from minus L to L. So that's just the length. The length there's L minus L is 2L. Then the L's cancel. And so we get to m. Now if you check the left and right end here, I have what we've shown is that a sub n is less than or equal to 2n. So we've proved this claim right here. And it's not necessarily surprising because we've said we're only going to consider functions that are piecewise smooth. And so that means we're only going to consider functions that are piecewise continuous, whose derivative is piecewise continuous. And if you say the function has to be piecewise continuous, then you're saying, oh, we're not allowing any infinite discontinuities. So it's it's reasonable the function is bounded, and certainly its integral is bounded. Certainly when you multiply by cosine, which is a bounded function, that will still be bounded. So we can use the same argument to show b sub n is less than 2n. Nothing is different. You just change the cosine to a sine, but everything identical. And a sub 0, that just follows directly because a sub 0 is just 1 over 2L integral from minus L to L of f of x. And so you take the absolute value, bring it inside, replace this part with an m, integrate that, you'll get 2LM, but remember for a sub 0, we normalize by dividing by 2L, so you just get m back as its upper bound. So that's a very straightforward, for a sub 0, it's very straightforward. You don't have to worry about a cosine or sine term. So take a second, maybe rewind this and go through this argument again. As I said, very important is this identity. So make sure you go through the argument of how we establish that. And as I said, there's no, it's just manipulating inequalities and basic properties of integrals. And so we can, by using properties of the absolute value, we can establish this inequality here. The absolute value of the integral is less than or equal to the integral of the absolute value of the function. Okay, so now let's finally prove the fourth and final claim, and perhaps we'll see why we needed f prime to be piecewise continuous. So far, we've only required f to be piecewise continuous so that the integral of f makes sense in the case of the a sub n and b sub n coefficients, as well as in the case of a sub 0. Okay, so here we assume that f of x satisfies restriction number 1 and or restriction number 2. Really, I just like to think of it as restriction number 2. Because if it's equal at the endpoints and you average, you still get the same values at the endpoints. If it's not equal at the endpoints, then you want to average. So now we want to show, look, a sub n, b sub n coefficients actually go to 0. If they don't go to 0, this Fourier series doesn't even have the possibility of convergence. But be careful, the coefficients going to 0 isn't enough to guarantee convergence. So that's what convergence part 2. So we'll talk about the actual convergence of the Fourier series, to the function, because that's what we want to know. Beyond convergence, does it also converge to the function? So we'll talk about that in lecture 5, L05. So suppose we have the periodic extension of our function called f tilde, and this may be adjusted or not, adjusted if necessary. Suppose that's piecewise smooth on minus L to L. Again, the periodic nature of the periodic extension will then imply this piecewise smooth behavior extends forever. But we don't care. We're going to start here. So now there may be points where either f of x or f prime of x have discontinuities because they're piecewise smooth. So they're piecewise continuous at best. We weren't requiring that they be continuous. And remember, where they do have a discontinuity, it would either be a removable or jump. So let's call these discontinuities of either function, either the function f tilde of x or its derivative. We're going to denote any discontinuity. We're going to list them all. And so here, suppose there's capital N discontinuities of either f of x or f prime of x. So we've listed them as x1 through xn. So let me draw a little x-axis here. So if this is our little x-axis, and let's say that's minus L, this is L. So we're going to call minus L x sub 0. And here, suppose we have capital N discontinuities of either function, f, the periodic extension of f, or its derivative. And so suppose these are the points where it has its discontinuities. So I'll just draw 3 points just for the sake of being easy to draw a diagram. So here we will call this then, this would be x sub 1, x sub 2, And let's say this is the last one. Sorry, this should be an x of n, and down here, this should be an n plus 1. My bad. This should be an n plus 1. So yeah, these are the possible discontinuities of the function or its derivative. I won't draw a function. So that's what we've got. And so now we want to break up the integral. We're going to integrate from minus L to L. But what I'm going to do is I'm going to break it up. In this case, it would be 3 integrals from minus x sub 0 to x1, x1 to x2, x2 to this last point here, and then this final integral. So that's what we do right here in this first step. The integral from minus L to L, we break it up. This is now an integral. So x sub p minus 1 to x sub p is one of these subintervals down here. And we're just adding them all up from 1 to, the index is worked out so that it's all correct. So when p is 1, this starts at x sub 0, which is negative L, and it goes through. And when p is capital N plus 1, this will be x sub capital N to x sub capital N plus 1, and x sub capital N plus 1 is capital L. So it's the index is worked out, so that's all correct. So we break up the integral into these smaller subintegrals where the bounds are the points of discontinuity of either function. And, we've listed them, just as they appear on the x-axis from smallest to largest. And so now we have these n plus 1 integrals. So here we brought the 1 over capital L inside all the way to here. And now we have this integral, which looks like a sub n, except we're not integrating from minus L to L. It's these smaller subintervals. And there's n plus 1 of them. And so now it's a little irritating, but we're going to introduce some notation so that we don't have to write this over and over again. What I want to show you now is that the alpha, that each of these integrals, or the sum when you send n to infinity, goes to 0. So here, let's introduce some notation. So we're going to call this integral here, we're going to call it alpha sub n comma p. So what does all that mean? The sub n is referring here to the mode of the basis. The alpha is like a, because this is the a sub n term. Alpha is like a. The n is referring to the mode, and the p is referring to which subinterval we're integrating over. So if alpha n sub p, I know that we're integrating from the x sub p minus 1 to x sub p. And now p will be a number between 1 and n plus 1, or whatever is appropriate. So now let's look at this integral. So here I wrote it explicitly. So the integral, each of these integrals over the subintervals we're calling alpha sub n instead of a sub n. And the p indicates which subinterval we're over. So, okay. So now we're going to use integration by parts. And now you'll see why we need the piecewise smooth, why we need f tilde prime to also be piecewise continuous. So for my integration by parts, I've written how I'm choosing the u and the dv. So let u be the f tilde x, and let dv be cosine n pi x over L dx. So remember how this works. Integration by parts formula says the integral of u dv equals uv minus v du. And so that's what I've done here. I take the integral using integration by parts. There's the uv, so uv minus v du. And so if dv is this function here, cosine n pi x over L, let's do this slowly now. We're going to integrate. The integral will be sine n pi x over L, and then we have to divide by this constant in here. We have to divide by L. We have to divide by n pi over L, so we'll be multiplying by L over n pi. So here's what we get. There's u. Here's v. the integral of cosine n pi x over L. So the integral would be this expression right here. So just take a look. Let's just go the other way. Let's take a derivative, right? So let's start with this function and let's take derivative. We should be able to get back. So derivative sine n pi x over L is cosine n pi x over L times chain rule says derivative of the inside, which is n pi over L. But we've got an L over n pi, so those cancel. That gets me back to cosine n pi x over L. So that's the correct integral. And right here, we need minus v du. And so this is why we need f prime to be piecewise continuous. When we do the v du, so here's v and then du. For the integral of f prime here to make sense, we would need, this function f prime times sine. We would need that function to be at least piecewise continuous and bounded. And so we know sine is continuous and bounded, so we know sine's not the issue. So here, for this integral to work, we need this expression, derivative of f tilde prime, which is related to the function f, it's just the periodic extension. We need that function to be piecewise continuous, so this integral makes sense. So for the a sub n terms, we need f of x to be piecewise continuous, and to be able to do this integration by parts, which is a key step in doing the in showing that these sequences go to zero. We need to be able to do this integral, so that's why we need f prime to also be piecewise continuous. So now we have f has to be piecewise continuous, f prime has to be piecewise continuous. That's why we're requiring f to be piecewise smooth here as part of our assumptions. And so, of course, the other assumption is that it's averaged at the endpoints. Okay. So now something very important happens that we have to keep track of. Here I have an L over n pi. Here I have an L over n pi. So I can now factor out this L over n pi. And this is so important. This is what makes everything work. And think about, where did this L over n pi term come from? It's a result of the integration by parts. It's a result of integrating the dv portion, which is right here. When we integrate the dv portion to get v, you get this L over n. Okay, and keep this in mind, because say this is really important, because this is what's going to make everything work. So yeah, I factor out the L over n pi from both terms, factor it out, and multiply by 1 over L, so the L cancels. So this gets factored out, and you just get 1 over n pi. And so that's what we have right here. Oops, sorry. Little zoom's messing with me. So right here, this 1 over n pi, that's where that comes from. Factor out the L over n pi. There's already a 1 over L there. The L's cancel. I just have a 1 over n pi. So now, what I want to show you is when we send n to infinity, this whole term will go to 0. That is, when I send n to infinity, alpha n will go to 0. And that'll be true for every p. So for all of these subintegrals. So this integral here will go to 0. So a sub n will go to 0. So that's the game plan now. I want to show you this expression at the bottom is going to go to 0. So the first thing I'm going to do is take an absolute value, because on the next slide, what I'm going to do is take an absolute value like this and use a triangle inequality. So I'm going to take absolute value and then use a triangle inequality and try and break this up into a sum of absolute values. So here, let me just remind you of the triangle inequality. There's the triangle inequality, but it could work with minus signs too. So if I had absolute value of a minus b, Well, I just think of this as A plus quantity negative B, and then apply a triangle inequality, which I believe we proved. So then triangle inequality, we say this is less than or equal to absolute value of A plus absolute value of negative B, but the absolute value of negative B is just the same as the absolute value of B. So we can apply triangle inequality to absolute value of A minus B as well, not just, absolute value of A plus B. That can be a minus sign too. Okay, so what we're going to do is take the absolute value of both sides, use triangle inequality, and then on the integral, we're going to bring the absolute value in. Okay, so couple of techniques here, and this is just good old-fashioned analysis. So this is the kind of thing you'll do a lot in an analysis class. Apply a triangle inequality, bring the absolute values inside, and try and bound the function. So first step, okay, so be careful, make sure you can see what's happening here. We have this one gigantic term inside the absolute value. Now, I'm going to triangle inequality, and see now we have three terms. So this term is inside an absolute value. This term is inside an absolute value. And here we have the absolute value of the integral, but then we use the identity and said the absolute value of the integral is less than the integral of the absolute value. So that's where this term's coming from. And all these minuses kind of got absorbed by the absolute value. And in triangle inequality, they got converted basically because they got absorbed into the absolute value, and triangle inequality puts pluses there. So we have the sum of three terms now where each individual term is in an absolute value. So take a second to look at that. So here, all these terms are in the absolute value brackets. And then we bring the absolute value brackets inside, distribute essentially to each term. And so now I have three terms: absolute value of that, absolute value of that, plus integral of the absolute value of that. Okay, now I'm going to write the absolute value of the product as the product of the absolute values. And so here, for example, in this first term, I have the absolute value of f tilde xp times sine of n pi xp over L. I can write that as the absolute value of f tilde times the absolute value of sine. And then the sine term, this part, so I can have absolute value here. And then the sine part is less than or equal to 1. So it'll look like I just made it disappear, but that's not what happened. I bounded it with a 1. So you should imagine there's a times 1 here. And that's bounding the sine term. Let's say I have this less than or equal to here. So this is from triangle inequality. And here I'm bounding the sine terms. And so that we do that 3 times to this first term, the second term here, as well as this term in the integral. Right, the absolute value of the product is the product of the absolute values, and then bound the absolute value of sine by 1. So imagine this is being multiplied by a 1. Right? Finally, we say all of these functions are bounded. Like this is just the function value at a single point. So we know the function is piecewise continuous. It's defined here because at a point of discontinuity, it's either a removable discontinuity or a jump discontinuity. Here it's again bounded, and again this function is bounded in this interval because we don't allow any infinite discontinuities. That's really, the definition of piecewise smooth. The piecewise continuous part for the function and the derivative makes it so that the functions are nice and bounded and the integrals of the functions are nice and bounded. It doesn't allow any infinite discontinuities. So I can bound this entire term by some constant that I'm going to call C. And so here, I'd say the boundedness comes from the fact that we're on a closed interval and that they're both piecewise continuous functions. And so we've basically proved that the integral, the subintegral here, alpha sub np, the absolute value of it, is less than or equal to a constant divided by n over pi. The constant and the pi don't matter. What matters now is this n term. When we send n to infinity, we know 1 over n goes to 0. We know 1 over n will decay to 0 kind of slowly as n goes to infinity. So here we send n to infinity on both sides. We conclude that this subintegral alpha n sub p. So hold on, let's go back one slide here and look at the subintegral. Remember, we're really looking at this integral, which is the formula for the coefficient. We've taken that integral and broken it down into n plus 1 subintegrals. Here's the subintegral, and there's n plus 1 of them. And now we're showing for every subintegral, as you send n to infinity, the little n, not capital N. So here, be careful. We're sending this n right here to infinity. We're sending this n right here to infinity. Because that's the term that appears. Remember, our series is like sigma a sub n times cosine, and here the n goes from 1 to infinity, right? And there's like cosine stuff here, blah, blah, blah. So that's the n we're sending to infinity, okay? Send that, we're showing if you send that n to infinity, the subintegral goes to 0. So the sum of the n plus 1 subintegrals goes to 0. That is, a sub n goes to 0 because a sub n is equal to the sum of these subintegrals. A sub n is the integral from minus L to L. If you add all these integrals, these subintegrals, you get an integral from minus L to L. So a sub n, in fact, is going to 0. And it's a similar proof for b sub n. You just replace the cosines with sines. Everything works exactly the same way. So it's kind of not satisfying almost too technical, because that's all it is, a very technical result. Have we really learned anything? We've learned some good technique. Like here, what's super important to me is when we use this integration by parts right here on this term, never mind whether you split up the integral or not. If you do an integration by parts on this function, you'll get a similar behavior, okay? When we do integration by parts, we get this L over n pi term that appears in both terms. And that's so crucial now because then we factor out that term. And it's now a 1 over n pi term that's multiplying the whole thing. And this is the thing that goes to 0 when you send n to infinity. The only thing, we had to check was that none of these terms in the brackets here was itself blowing up to infinity. Then you get like an infinity over infinity type thing, and then more analysis needs to be done. So what we finally did after the integration by parts is just to check that this part that I've highlighted here inside the brackets is bounded. And then when we send n to infinity, this term here goes to 0, thereby shutting down, all of the sub-integrals or sub-parts of a sub n. So from a technique point of view, it's important to see how the integration by parts gives us this n in the denominator. It would be nice if we could get an n squared. That's a little stronger. 1 over n goes to 0, but very slowly, and the harmonic series diverges. So this sends us to 0, but I wish it was faster. Perhaps if we could do a second integration by parts, we might be able to get an n squared, but a second integration by parts would require f double prime be piecewise continuous. So for that stronger integration that I'm hoping for, if I could try and do a second integration by parts, I'd need a function with more regularity than I'm specifying right now. So anyway, as of right now, we get this 1 over n pi using integration by parts once, and that 1 over n pi, once we bound the rest of it, is the whole reason we're able to conclude that the subintegral goes to 0 as n goes to infinity. This part here will shut down to 0. And so, a sub n has to go to 0. Alpha a sub np has to go to 0, so a sub n has to go to 0. So yes, as I said, an exact similar proof can be used to show that b sub n goes to 0 as n goes to infinity. This does not prove convergence of the Fourier series. This proves convergence is possible, which is huge. So if we're looking at the Fourier series of a piecewise continuous function, we can prove that convergence is possible. And as I said in the next set of lectures, we'll prove the pointwise convergence of these piecewise smooth functions. So what's going on when a sub n goes to 0? I want you to think about the geometry of that. So here I did a picture that involves a b sub n term. So you remember the formula for b sub n is b sub n, and then we have our 1 over L. And then we integrate from minus L to L. And now we have f of x times, and now we've got, I should have just done this on minus pi to pi just to keep it simple, but whatever. Okay, sine, and then this will be n pi x over L. Okay, so dx. So what we're doing, when you send n to infinity, think about what's happening. This part's really important, so take it slow. We're sending this term here to infinity. When we send n to infinity, we're saying send this to infinity. What we're doing is we're multiplying f of x, so that's the same term n here, okay? And remember, that's what appears in our series. It's sigma b sub n times sine blah, 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 and then n goes from 1 to infinity. Okay, that's the n. And we're looking for larger and larger values of n, what's going on with this coefficient. So think about the geometry. Think about this from a Calc 1 point of view in terms of areas. We've got this function, f of x times sine of n pi x over L, which I've graphed here. I think I used x squared or something for the function. And I'm doing, here I did sine 4 pi x over L. So here, this is an example where n is 4. And you see, it's this function that dips up, up and down, goes up and down here around the x-axis because of the sine function, which is oscillating. So now, when we calculate the integral, remember your Calc 1 tells us we're calculating the net area. We're taking all the areas above the curve, and we're subtracting that area from all the areas below the curve. So I have area above the curve minus area below the curve. And as we send n to infinity, the amplitude doesn't change, the frequency changes. So what would the picture look like for f of x times sine of 5 pi x over L? It would be a curve where it's more frequent. So here, for a higher n number, so here, I don't know how to draw this, but you'd have more frequency here, right? And it's, as n goes to infinity, this thing in here just gets more and more frequent, as a sine curve. I can't draw it with my human hand, but it gets more and more frequent, squashed together as n goes to infinity. Think about n being really large. That means your period is 2 pi over n. As n goes to infinity, 2 pi over n goes to 0. So as n goes to infinity, you're looking at a sine function with the period is almost 0. So it's just like repeating itself so many times, So what it's saying is as n goes to infinity, the area above and the area below completely cancel out, which is really remarkable to me. Think about this in the Calc 1 way. B sub n is an integral. So the integral is the areas. So here when we say b sub n goes to 0 as n goes to infinity, as this curve becomes more and more frequent, it starts to, wiggle up and down more and more. The area and the above and below somehow balance out perfectly and cancel out completely. To me, that's a remarkable result. I mean, there's no reason why that should be true. So in this picture, it looks reasonable because you go, oh, these two will cancel out. That seems reasonable. And these two will cancel out. That seems reasonable. But there's no reason the picture needs to look nice and symmetric. There's no reason. And so to me, it's really remarkable. It's known as oscillatory cancellation. And here, because of the oscillatory cancellation in the Fourier series coefficients, we're able to show that the coefficients go to zero. So this is a required conditions for convergence, but does not guarantee it. And this result of oscillatory convergence, which, as I said, shows that convergence is possible but not guaranteed, is a special case of this important theorem known as the Riemann-Lebesgue lemma, which comes up in a big way in complex analysis. It has to do with how these oscillatory functions behave. And sort of more general statement of the result is if we have some piecewise smooth function, say q of z, and we take q of z and multiply it to cosine mz, for example, and then integrate that and send m to infinity, then because of this oscillatory cancellation, the net area, the integral, integrates to zero as m goes to infinity. And similarly, if you multiply by sine. So think about, take q, multiply by sine, that gives you an oscillating function that oscillates above and below the x-axis. Then you integrate that. So you're calculating the net area. You take the area above and the area below, subtracting those, calculating the net area. The theorem says as m goes to infinity, as we get this maximum frequency, the period's going to zero, you get perfect cancellation of the area above and below. You get oscillatory cancellation. So that to me is a remarkable result. And we've proved a very kind of light version of it here. And there's certainly more general versions of it that even extend to complex numbers and stuff like that. Of course, we won't talk about all that. Okay, so that ends the lecture. Thank you for your time. Please perhaps watch the lecture again as necessary. And thank you for your time, everybody, and take care.